If you come to the session 3, well, now we give an analytical functions. What's an analytical functions? A function f of z which is one valued and differentiable at any point z naught is said to be an analytic function. The point z, analytical function of the point. See, if you take a complex circle, so if a differentiable at a point, something a point is derivable all a neighborhood of that points. That is called analytical function. Analytical functions. See, if analytical functions is if you take if a z naught is a differentiable is derivable at all neighborhoods of z naught. That is called analytical functions. Now, yeah, see, a function f of z which is one valued and is differentiable at any point z naught is said to be analytical at a point z. If function is analytic at every point z of a certain domain D, it is said to be analytic is in that domain. Analytic means is a derivable all neighbors of that points. A function f of z is may be differentiable in a domain except a possible for finite number of points. These points are called singular point or singularity of f of z in a domain. If a finite number of points, certainly is called singular points. We come to the definition of analytic function. See, if you take a unit circle in a unit domain, with a complex unit domain, a function f of z of a complex variable z is said to be analytical at a point z naught. If f of z is differentiable not only at z naught but at each point in some neighborhood of z naught. That's why I'm explaining in that. So differentiable at all neighborhood of z naught means differentiable at neighborhood of z naught. A function f of z is analytical in a domain D if it is analytical each point of D. The word used synonymous with the word analytic are holomorphic or regular. Holomorphic and regular. If a function f of z is analytic in every neighborhood of a point z naught except at z naught itself, z naught is called isolated singularity of f of z. Isolated singularity of z means if you isolate it like this, z to a neighborhood of z naught, z naught to neighborhood of z naught, z naught. This is called isolated neighborhood of z naught. Means isolated like this. This is called means is holomorphic. A single isolated means holomorphic. Regular is unit complex type. See, in that we come to the theorem. What is necessary and sufficient condition for f of z to be analytic? See, necessary and sufficient condition for analytic function, the partial derivative of real part of ux is imaginary part of v1. So, here imaginary part of that minus times of real part of that next time. Means, if a function f of z equal to u of xy plus I v of xy is analytical in a domain D, the partial derivative ux, vx, uy, vy should exist and satisfy the equations ux is equal to vy, uy is equal to minus times of vx. Means the proof of by data f of z equal to u of xy plus I v of xy is analytical in a domain. See, if you take a z, what is z? Is complex number x plus iy. If it changes real and imaginary term, very instantaneously small. If you changes x variable and y variables are exact real term and imaginary very instantly, the complex number is also changed. Means if you take delta z equal to x plus delta x, comma r plus I times of y plus delta y, like that. Means delta z equal to delta x plus I delta y. Means if you change that, if we express in a complex form of u of xy plus iv of xy, if we change just that f of z equal to z plus delta z, here equal to u of x plus delta x comma y plus delta y plus I times of v of x plus delta x comma y plus delta y. So if it changes the complex real and imaginary term is also complex number totally changes. If we take number, so if a function f of z equal to u of xy plus iv of xy is analytical in a domain D, therefore derivative, you know the definitions of derivable function. Derivative of f of z equal to limit delta z tends to 0, f of z plus delta z minus f of z divided by delta z. I'll call this equation as 1 by using the definition of derivable functions. Now each unique exists a unique irrespective of a path in which delta z tends to 0. Now, if f of z equal to u of x comma y plus I v of xy equal to, if it changes, f of z plus delta z equal to u of x plus delta x comma y plus delta y plus I times of v of x plus delta x comma y plus delta y. If you take z equal to x plus I y, delta z equal to delta x plus I delta y, means very extension changes is also where delta z is changes. Now, if we replace, so what is the partial derivative? If you take derivative of f of z equal to limit delta z tends to 0, u of x plus delta x comma y plus delta y plus I v of x plus delta x y plus delta y minus u of xy plus I v of xy divided by delta x plus I delta y. Let delta z be all real. If you take a delta z to be totally real, imaginary terms is 0. So delta z equal to delta x. So derivative of f of z should be equal to limit delta x tends to 0, u of x plus delta x, y plus delta y plus I v of x plus delta x, y plus delta y minus u of xy plus I v of x. So I replace this total functions is changes z replace delta z replace delta x plus I delta y, x replace I plus delta x replace x plus delta x, y replace y plus delta y. Similarly, changes the variables, the instance changes the variable, so function we are changes. So if a limit delta x tends to 0, u of x plus delta x comma y, because delta y is 0 because you are taking the real axis, minus u of xy divided by delta x plus limit delta x tends to 0, I times of v of x plus delta x y minus v xy divided by delta x. You are taking the separately real term and imaginary term. So by the definitions, the limit of the definition and also continuity definitions, whatever may be there, the derivative of the definitions, the first term simply write del u by del x plus second term is I times of del v by del x. Del v by del x. We call that equation 1. Again, if we take delta z tends to 0 along the imaginary axis, a delta z all imaginary, we replace delta x equal to 0. Now delta z become I times of delta y. So derivative of f of z is equal to limit delta y tends to 0, u of x comma y plus delta y plus I times of v of x comma y plus delta y minus u of x comma y plus I times of v of x comma y divided by I delta y. Now we come to the real and separating real and imaginary part in the numerator. Also, what you get, u of x y plus delta y minus u of xy plus I times of limit delta y tends to 0 but I times of v of x comma y plus delta y minus v of xy divided by I delta y. Now take 1 by I times of, by the definition of by the definition of derivative, we write del u by del y in the first term plus I times of I get cancels here, we get del v by del y. So I call this equations 2. Again, since partial derivative f of z is that, so we come to that. If instead of 1 by I, we take a numerator I, means numerator I am multiplying that I square, one time get cancelled, we take I in the numerator, we get minus I del u by del y plus del v by del y. We call this equations. So, in comparing 1 and 2, comparing that, or in the right hand side. So left hand side are equal. So comparing the right hand side, so 1 and you are equating. So right and left hand side are equal. Now compared to the right hand side, del u by del x plus I times of del v by del x is equal to minus I times of del u by del y plus del v by del y. Now again comparing real part and imaginary part. So del u by del x is equal to del v by del y. So imagine del v by del x is equal to minus times of del u by del y. So really we can write ux is equal to vy, uy is equal to minus vx, a partial derivative condition. Hence the theorem. These equations are known as Cauchy-Riemann partial differential equations. Simply say Cauchy-Riemann equation or CR equations. So this is a necessary conditions. If we come to the sufficient condition, f of z to be analytic, we have the above that the theorem is true. The Cauchy-Riemann equations is the necessity condition for function to be analytic. Now, but it is not a sufficient condition. But it's not a sufficient condition. What is the further required? For partial derivative ux, vy, uy, vy must exist and must be continuous at all point of the region. Must continuous at all point of the region. We have already solved the above Cauchy-Riemann equations are true. The four partial derivative ux, uy, vx, vy exist. Assume further that they are continuous. Again we go for del u equal to u of x plus delta x, y plus delta y, a minus u of x, y. Again we come to the u of x plus delta x, y plus delta y minus u of x plus delta x, y plus u of x plus delta x, comma y. You are adding u of x plus delta x, y plus adding and subtracting u of x plus delta x, y. And we are again separating that equations. We are at the four partial derivatives continuous. Yeah, again I am saying here the function u of f of z equal to u of xy plus iv of xy is analytic in domain D. If the four partial derivatives are also continuous in domain D, u and v are differentiable in the domain D. Ux equal to u vy, uy equal to minus vx. So CR equations are satisfied at each point of D. Now again what is the necessity condition or sufficient? By using necessity condition, what is the sufficient condition required? Means del u by del x and del u by del y are supposed to be continuous. Each partial derivative. Suppose del u is equal to u of x plus delta x, comma y plus delta y minus ux, u of x, y. So again u of x plus delta x, y plus delta y minus u of x, comma y plus delta y plus u of x, comma y plus delta y minus ux. Here u of x, y plus delta y plus u of x, y plus delta y add and subtract. But again we are first derivative we can del u by del x plus epsilon 1 times of delta x plus del u by del y plus mu times 1 of delta y is equal to del u by del x into del x plus del u by del y into del y plus epsilon 1 del x plus mu 1 del y. Now we are taking sum and that we can write. Now there epsilon 1 tends to 0 and mu 1 tends to 0 as delta x tends to 0 and delta y tends to 0. Similar, since del u by del x and del u by del y are supposed to be continuous, we have so del u by del x plus epsilon 2 plus del u v by del y plus epsilon 2 del y is equal to del v by del x delta x plus del v by del y delta y plus epsilon 2 times of del x plus epsilon 2 times of delta y. So here epsilon 1 tends to 0 we get. Now suppose if we take where epsilon 2 tends to 0 and mu 2 tends to 0 as delta x tends to 0 and delta y tends to 0. Again u of x plus delta x, comma y plus delta y plus I times of v of x plus delta x, comma y plus delta y minus u of xy plus I v of xy. This is equal to del u plus I times del v. Now again separating dividing del u by del x plus I times of del v by del x into delta x plus del u by del y plus I times of del v by del y delta y is equal to plus epsilon times of del x plus mu times of del y. You call this equation as 1. Now this is your epsilon can be expressed in complex form. So epsilon can be right in complex form is complex form epsilon 1 plus I times of epsilon 2. Again mu is a complex form. Again mu can be written as mu1 plus I times of mu2. This tends to, if delta z tends to 0, mean like that, epsilon tends to 0 means epsilon is equal to epsilon 1 plus I times of epsilon 2 tends to 0. mu1 is equal to mu1 plus I times of mu2 tends to 0 means delta x tends to 0, delta y tends to 0. By Cauchy-Riemann equation, one can be written as in the left hand side f of z plus delta z minus f of z equal to delta u by delta x plus I times of delta v by delta x whole divided into delta x plus minus times of delta v by delta x plus I times of delta u by delta x of delta y plus epsilon delta x plus mu times of delta y. So again we are collecting is a real and imaginary part like that. Delta u by delta x plus I times of delta v by delta x of taking delta u by delta x plus I delta v by delta x as a common. We get delta x plus I times of delta y because we are taking I into I square is minus 1. Instead of minus 1 we can write I. Instead of minus 1 you can write I square. I square if you take one term is outside or I keep other term as it is. So delta x plus I times of delta y plus epsilon delta x plus mu times of delta y. So again we are dividing by delta x plus I delta y is equal to delta z. By taking the limit delta z tends to 0. We see that limit delta z tends to 0 f of z plus delta z minus f of z divided by delta z. We come to the definitions of derivative form. Limit delta z tends to 0 means dividing throughout by delta z. Now dividing throughout by delta z, simultaneously applying the limit delta z tends to 0 f of z plus delta z minus f of z divided by delta z equal to, this means a derivative of f of z means f of z equal to right hand side we get delta u by delta x plus I times of delta v by delta x. So that the derivative exists and unique. So f of z is analytic in a domain D. So whole means this is your derivable. It's a neighborhood of a z naught. It's a neighborhood of in a complex plane in a z naught. This is the differentiable in the neighborhoods of z. This is called analytic work. So this is true, necessary and sufficient condition. This is true. This is called Cauchy-Riemann equations, or simply say Cauchy or differential equations.